So last Tuesday, we considered an example on how to work out the character table of the group S3. So that's the permutation group of 3 objects. So I would like to consider 2 more examples, in a way simpler. So let's go through this. Let me remove the video here. So the next example I would like to consider is an abelian group with just 4 elements. So remember that an abelian group means that the elements commute with each other. So then each element forms a class by itself. So this is because you have, let's say, AG is equal to GA. So then G minus 1 is equal to itself for any G. So then an element A is always brought to itself by this similarity transformation. So each element forms a class by itself. So this also implies that since the number of irreducible representations is equal to the number of elements, or the number of classes, which is the number of elements, then the only possibility is to have a one-dimensional representation. So all irreducible representations have dimension 1. So let's consider a particular abelian group, like the one we have here. So this is the multiplication table. And we have a squared equal to b squared and equal to c squared. That's equal to the unit element. So a characteristic of abelian group is that the multiplication table is symmetric because of this commutativity. So as you can see that the multiplication table is symmetric. So now let's try to construct the character table of this group. So we have 4 of this, and we have more here, like this. So these are the elements and the representation T1, T2, T3, T4, like that. So as usual, we can fill in already the first row. So that's easy. And we also know that the dimension is 1. So then we can also fill in the column. So that's 1, 1. So I guess these are the dimension. So now we just have to fill in the rest of the characters. So a squared is equal to b squared equal to c squared is equal to e. So that would imply that we can only have a or b and c and so on equal to plus or minus 1. So if a equal to 1, then b or c should be equal to plus or minus 1, like this. And if a is equal to minus 1, then we have to be a bit careful here, because if b is equal to equal to 1, then c is equal to minus 1. So if this is minus 1 here. and so on. So we just fill in the character table. So if this is equal to 1, then say if a is equal to 1, then we know from the orthogonality of the characters. So we take these two columns, then we know that this should be equal to -1 and -1. Yeah. And the same here. So we have -1 and -1 because of the orthogonality. And the rest can be easily filled in. So this has to be 1, then this should be -1, and this is -1 and 1. So this is the character table. It's quite simple because it's an abelian group. So let's consider another example. Let me erase this. So another particular group that has a kind of well-defined character table is the cyclic groups. The cyclic groups are also abelian. So we recall that a cyclic group means that the elements can be generated from a single element. So in this case, we take A here, we take A, then all the elements are just the power of these elements. So that A to the H, which is the order of the group, or the number of elements in the group, is equal to 1, or E. Yes. So since it is abelian, it's also very simple. So here actually we can get a general solution. So if we take AK to represent the element A, even element A, then we know that A to the K power of H is then must be just equal to 1. So then the AK must be the roots of unity. So then we know the solution. So this is just given by the exponential of 2 pi k divided by h. That is the solution. Because the characters can be complex, so these are the solution to the representations. And it is quite straightforward to just fill in the character table like we have here. So if you have done solid state physics, for example, you recognize that this is like the phase factor in Bloch theorem. You know, if you have a solid and you have the Bloch state is labeled by k, you can write as k dot r uk r like that. So this k here is the same as that k because the translational groups are abelian, and if we use the so-called Born-von-Karman boundary conditions, and it's also cyclic, so we have these properties here. It's just a remark. Okay, so now we have done all the necessary tools we need to apply group theory in quantum mechanics. So we said in the very beginning of the course that there are a number of important applications of group theory in quantum mechanics. So let me just repeat a little bit of that so we get some a clear idea of what we are heading for. So one of these is diagonalizing Hamiltonian. So we have a Hamiltonian of a given system. We're usually interested in finding the eigenstates and eigenvalues of that system. So we introduce some basis functions. So we have a matrix like this, and we want to diagonalize. Now, of course, we can just use basis functions, calculate Hamiltonian matrix, and diagonalize it. But in practice, this matrix can be very large, can be thousands or even tens of thousands. So group theory, if the Hamiltonian has certain symmetries, that group theory can be used to simplify this diagonalization. And this is done by classifying the basis functions according to the irreducible representations of the group. So we will do this. Second major applications is to finding normal modes, vibrational normal modes. So normal modes of vibrations. So I'm thinking about molecular or crystal vibrations here. So again, here one can classify the normal modes of the vibrations according to the irreducible representations of the symmetry group. So here, if you have done some solid state physics course, you remember you have, when you do phonons, you have this dynamical matrix. Dynamical matrix that you want to diagonalize to get the normal modes. So in a way, it is similar to the first case, that's diagonalizing Hamiltonian. So one can classify the basis for this dynamical matrix according to the irreducible representations of the group. The third problem is third application. This is more kind of qualitative. This will be the splitting of degenerate states. So this is a broken symmetry things. So we have states which are degenerate. So if you recall that symmetry usually implies some degeneracies. So now if you reduce the symmetry, or you break the symmetry to a lower symmetry, then these states can be split into several states. And group theory then can be used to classify how these states are split into the different irreducible representations of the lower group. And fourth applications is the applications of calculating matrix elements. So in quantum mechanics, we always have to compute matrix elements of some operator between the two states. So this is actually known as the Wigner-Eckart theorem. Wigner-Eckart theorem. So I think you also do this in quantum mechanics, but usually in quantum mechanics you specifically talk about quantum angular momentum states. But here we do not specify states, so these are just very general. So again, the group theory can be used to simplify these calculations or help us calculate these matrix elements. So the common denominator of all these applications, and then there may be some more. So the common denominator is really just a matter of of classifying the basis functions, or the states. Maybe I should just say classifying states and operators also in the case of the Wigner-Eckhart theorem according to the irreducible representations of the group, of course, of the symmetry group. So this is basically the common denominator, the basic thing that we have to do in all of these problems. Okay, so we first need to define how the symmetry operators or so how the symmetry operators act on an arbitrary function. So we want to know this coordinate transformation. It's a length preserving coordinate transformation, G. So this is a bit like rotation then. In most cases, it's really just rotations of the coordinate systems. We define it this way. So if I operate it, this symmetry operator on the position, then it's just rotating the vector or by the element G. So G can be a rotation operator. So it is usually just a rotation operator. So we have this matrix equation. So if I have a general state, call it F here, then we want to know what is F prime. So that's the function that we get, or the state that we get when we apply the symmetry operator on the state F. So we want to know this in the position representation. So we look at the position representation, then gives us the function F prime, and we want to see how the F prime is related to the original function. So we just compute this thing here, and then introduce a unit operator. One. So of course you have to integrate over R prime. So that is by definition just give me this GR prime. And this is just a dot product between two vectors, so I can bring the operation to the left, so that becomes the inverse. And then I can use the completeness. So then we get this f of g to the minus 1 r. Yes. So that's what happens when we rotate the function, the state, and then we look at the state at the position representation, then the function is just is equal to the original function, but with a coordinate rotated by g to the minus 1. So we use this shorthand. So this is a shorthand notation here. So we have that thing. We say that is equal to. So this is the shorthand notation. Yes. So this is the shorthand notation. So by itself it has no meaning, because t hat here is an operator in the abstract space, so we cannot apply it to some number like this. I don't know what it means, but it would be not so meaningful. But it is a shorthand. Yes. Because it's convenient to write it like this. So when we write like that, we mean this one here. So this is the proper way of writing that expression, and that is equal to the original function, but with a rotated coordinate. Okay, so this is just a definition. So what do we have next here? So symmetry transformations obviously form a group, because if I perform two symmetry operations on an object, the object always look the same. So then the product of two symmetry operations must be just another symmetry operations. So I think that's clear. We don't need to prove that. So symmetry operations form a group. So that is also why we study symmetry in conjunctions with group theory, because they form a group. Now, when it comes to basis function, so as we said in the beginning that we want to have basis functions to express or to construct our Hamiltonian and dynamical matrix and so on. So we want to consider some basis functions to represent our symmetry operators. So our symmetry operators is set of TG like this. This is an abstract operator. We want to, in practice, we need to introduce basis functions. Otherwise, we cannot calculate anything. So here we introduce the concept of invariant subspace. So subspace spanned by a set of vectors or functions, if you like. If you work in the position representations, set of functions is invariant under a given set of symmetry operations. So that's what we mean by invariant subspace. So if we apply the symmetry operator or any of this to one of these functions, then the resulting function remains in the subspace for all G and all of phi I. So that's why it's called invariant subspace, because the subspace goes back to itself when we apply the symmetry operations. So actually there is a very simple way of generating an invariant subspace. It's a very general way. So we can just take any function. Just take any function, f we call it, and we operate this function with the symmetry operators for all G, for all the elements in the group. Then the resulting functions form an invariant subspace. Well, this is kind of clear, because if I take any of these functions, so let's call this, let's say fi equal to tgif like this. Then if I multiply or operate this by another symmetry operator, then it will be just tg2, tg1, f. But this is, I need more space here. But this thing here, tg1 times tg2, or tg2 times tg1, is just another symmetry operation. Yes, so that is equal to, let's say, tg3. But tg3 acting on f is just f3, which is part of the subspace. So we see that it's an invariant subspace. Yes, it's clear. So generally, the number of independent functions that span this invariant subspace is less than or equal to the number of group elements. So when we form these functions by applying the symmetry operations on an arbitrary function, some of them can be the same, but some generally are different. So the number is independent functions is generally less or equal to. And in general, it is reducible. In general, this is reducible. As we will see this by considering an example later. Okay, so that's an invariant subspace that we need to construct a representation for the symmetry group operators. So now we have to introduce these basis functions. So we say that we have a set of functions of states fi that span an invariant subspace. And we assumed, of course, that these functions are linearly independent, but they don't need to be orthogonal or normalized. So we consider a very general set of functions. So if you have, let's say, in 2 dimensions, normally we use Cartesian coordinates like this. So this will be Ex and this is Ey like that. But of course, that's not necessary. We could also choose some arbitrary vectors like this and like this, as long as they span the 2-dimensional space and they form an invariant subspace of this 2-dimensional space. So we do not assume that they are orthogonal or normalized. Neither normalized. But we know that when we operate it, if we pick up a function, one of these functions fi, and then operate it with a symmetry operator, tg, then it has to be some linear combinations of the other functions in this invariant subspace. So these are just the coefficients of expansion of this state on the left-hand side. And this matrix it forms a representations for the group. So we can show this. So let's try to show this. Yeah, that. So we have what do we have here? So we have t. Let's say call it G2. Thing on Fi. So that we say is equal to sum over J J I G2. And now I apply again with T1. So that's why I call it G2. Because I want to apply G1. So then this becomes sum over J and call it K then. So then I have Fk. So now I'm applying this Tg1 on the Fj. So that becomes Fk Tk J G1 Tj I G2. So it's G1 here. So this thing is just another symmetry operator. So that's G1, G2. You can just call it G3 if you like. So then we have on the left hand side it's equal to sum over K of Fk Tki G1, G2. And the left and the right hand side is we have it as before. So we see that it is indeed form representations of the group. Yes, because this thing is equal to sum over j tkj g1 tji g2 like this. Yes. So we see that the basis functions need not be orthonormal. So they can have overlaps with each other, and they don't even need to be normalized. They form representations. And of course, the representations, if we choose some arbitrary functions like this, then they will not be unitary. And the representation is unitary if the basis functions are chosen to be orthonormal. So if I are orthonormal, then the representation is, then T is unitary. I think this can be seen quite easily. Okay, so this is what we have for the representations. We also sometimes need to consider a change of basis. So what do we have here? Yes, change of basis. This is just a simple thing. Basically what we do is we rotate the Hilbert space. If you think about this, phi I is forming the Hilbert space. And the rotation, of course, has to be represented by a unitary matrix. I think this is also clear. We already know this from quantum mechanics. Yes. So I guess I can skip this part. And we also have done this before. So the point is that if we make this change of basis by rotation affected by some unitary matrix S, then the new representation is related to the old one by this similarity transformations. So then the T prime and T are equivalent. So this is what we need so far. Okay, so let's clear this thing here. Yes. So now we come to a very important object here, the projection operator. So this is a very useful device in applying group theory to quantum mechanics, because this projection operators allows us to classify a given arbitrary function into its irreducible components. So if you think about representation, an arbitrary representation, T, this. In general, this representation is reducible, so it's possible to find some matrix. Yes, It's minus 1 here that brings the representations into block form. So these are the irreducible representations. Let's say, and there's a 0 here. So if we think about this matrix operating on some vector, then we see that we have a set of vectors here that corresponds to the alpha irreducible representations, and this one to the beta, and this one to the gamma. So you can see from the form of this matrix that all these alpha, beta, and gamma functions, they will not mix because this is 0. So there is no coupling between these vectors and these vectors here because of the form of the representations. They have a block form like this. So the idea is that if we have a given state or function, we want to decompose the functions into the various irreducible components. So we have given an arbitrary function or vector. We want to classify or decompose this function into the various components in the different irreducible representations. And this is the main point about projection operator. So let's see how do we construct this. I need to clear this first. Whiteboard. Okay. So I just follow the notes basically here. So we consider some set of functions or states. So this is assumed to span an irreducible subspace. So they transform according to the representation alpha. So this implies that if I operate it, if you take any function, say phi alpha I, then this is just a linear combination of the other functions. The coefficients are given by the representations of the symmetry operator, like that. So now we can make use of the orthogonality theorem. So this is where the theorems that we developed before will be used. So we multiply by complex conjugate, call it beta. So that's another irreducible representation. Call it KL here, like that. So I multiply both sides of the equations. Becomes J here, psi J. Okay, so these are just numbers, so I can put it here. KL like that, so for a given G also. And then we sum over the group elements. I need to have a sum also, so here over the group elements, because we want to make use of the orthogonality theorem. So when we sum over the G, then this gives us what do we get here? We get H upon L beta, and then there is the delta IL, so the column must be the same, and also the row, the JK, like this, and then there is also the orthogonality in the representation of a beta. So that is from the orthogonality theorem. So that we get, what do we get here? So we use that. So this becomes H upon L beta, and then delta IL delta alpha beta and psi k alpha. So I'm summing over the j, and then j is replaced with k. So we can define now this projection operator. Define the projection operator. So this is a definition here. Beta divided by h, sum over g, t beta star kl for g and t g. So we define this projection operator. So basically this is just this part here. So then we see that if we operate this projection operator on the state by alpha, so I'm looking at this thing here now, that is just equal to delta IL. So this constant disappears because I have included in the operator on the projection operator. This and psi k, call it beta. So it doesn't matter I have beta or alpha because I have this conical delta. Yeah. So we see that if beta is equal to alpha, then alpha k, yes, so if I put alpha beta equal to alpha, then I have pki acting on psi I alpha is equal to psi k alpha. Yes, so the L becomes I because of this conical delta here. So this has the form projection operator. So if I apply the projection operator on functions that belongs to a different irreducible representation, then this conical delta will annihilates that function. So the function must have the same, must belong to the same irreducible representations as this, as the one for the projection operator. So if alpha and beta are different, and then there will be 0. This will be 0 if alpha not equal to beta. So this is precisely the form of a projection operator because it picks up the component that that belongs to the irreducible representation. Okay, so let me check the time here. Oh, well, we already have finished. Okay, so maybe this is a good place to have a little break. And so we can start again at 11:15. And we continue with the projection operator. And in the other half, I would like to consider an example on how these projection operators are used, and also illustrate how we generate invariant subspace, and how we classify the basis functions according to the irreducible representations, by again considering our favorite example, this permutation group of three objects. Okay. I don't know if you have questions about what we've been talking about today. So if not, then we see again at 11:15. Okay, so I guess we can continue. So let's continue with this projection operator. So as we said before, that this projection operator picks up components of an arbitrary function. So if we apply this projection operator to an arbitrary function, then it will pick up the components belonging to the representation beta, and also this label here, k and the l. So in practice, we actually do not need such a detailed projection operator. We can construct a much simpler projection operator by taking the trace of this. So we take P, we define P beta here, and we take the trace of the projection operator. Like that. So then this is equal to L beta divided by H, sum over the group elements G, and chi beta star G T G, like this. So in most applications, I would say, we just need this projection operator instead of the more complicated one that we had before. It's sufficient to work with this projection operator. So this also shows again the importance of the character table, and the importance of character tables here you can see, because we need to know the characters of the various irreducible representations. That's why the character table is so important, because that allows us to do basically most of the things we need to apply group theory to real problems. So if we apply this P beta to some component like this, then this function phi alpha I must belong to the representation beta. So I will have a conical beta alpha like this. So that's exactly what we mean by projection operator. So in general, of course, we don't have a function that belongs to a particular irreducible representation and particular row. So we usually call this the row and the irreducible representation. The row, I don't know why it's called the row, not the column, but that's how they call it in most books. So if we have an arbitrary functions, well, I mean, we can always expand this in the various irreducible components like we described before. Yes. So we have these decompositions. So we should not confuse these components here with the basis functions. This just means that this is the component of phi belonging to alpha and I. Yes. So there is no connections between this component and the other components of this function, because they are not basis functions. So they are not basis functions. basis functions. So in general, actually, one could decompose even further because for a given arbitrary representation, let me clear this up here. So if I have an arbitrary representation T like this, so this is my matrix T. We can always bring it into a block form. So I could have a block form like this. So yes, I have 0. So it could be that the same representation appears twice. So I could have a T alpha here, and this is another T alpha, T beta, and so on. So that we could split the arbitrary functions, arbitrary vectors, and let's call it V. I can write it as the sum over the alpha I and T. T here labels the multiplicity of the same irreducible representations. So call it T like this. Say alpha T like that. So T can here for this example here, then the T can T equal to 1 here and T equal to 2, let's say. So we have multiple numbers of same irreducible representations. So I think this is clear. So the projection operator then allows us to pick up these components belonging to the particular irreducible representations corresponding to the projection operator. Now, before we do an example, there is another useful properties related to the orthogonality of the basis functions. So if we have two vectors, phi I, phi, and phi beta j, so these two functions, phi and psi, can be any functions. They are not related to each other. So the most important thing is that how they transform under the symmetry operations. So the actual form of the functions are completely arbitrary. So we have to think a little bit in the abstract here. So the theorem tells us that this the dot product of this phi alpha I and phi beta j is proportional to alpha beta and alpha ij. So if I have two functions, one belonging to irreducible representation alpha and belonging to row I, and another function is completely unrelated and belonging to beta and j, then they're orthogonal unless alpha equal to beta and I equal to j. So it's a very useful property. And we have to keep in mind that these functions are really arbitrary. They can be any functions. So the important point is that how they transform under the symmetry operations. So let's show this. So if I have particular symmetry operator operated on phi alpha, then this by definition is equal to, okay, so I have a set of functions that span the irreducible subspace alpha. Like that, and we can do the same with the psi. So this is why I call it psi difference to indicate that there can be completely different functions. I'll call this call it L. Okay. Just use the same notation as in the notes so I don't get confused. Okay, like this. So the representation is unitary. So this means that if you look at the dot product between these two functions, so that is just then the same as this dot product. Because I'm just rotating the same the function by the same symmetry operator, so then the dot product is not affected by this rotation. So this is then equal to, I just use this formula here, plug it in here. So that becomes sum over KL. So I just write out should be alpha here. J beta, and then I have the dot product between the alpha K and psi beta L, like this. So I just substitute this one with this one here. It's quite straightforward. So now I can use the orthogonality theorem. So to do that, I need to sum over the G. So sum over the G. But this quantity here is independent of G. So when I sum over G, then I have to divide by the number of group elements. So now I can use the orthogonality theorem for this part. That gives me, do I get this 1 upon L alpha, because I already have the H. And then I have d alpha beta, orthogonality, and then delta ij. And then I have also delta KL, and this thing. So then you sum here over KL. Oops. So now if I sum over the KL, then I get delta beta, delta ij, sum over K, phi beta, phi alpha, because anyway, beta must be equal to alpha, otherwise it's 0, so I can replace that with alpha. Okay, like this. Yeah, so that's what we have here. It's proportional to here, beta and ij. So if I have two functions belonging to two different irreducible representations and then two different belonging to two different rows, then they are orthogonal. So it's a useful property which comes entirely from symmetry. Okay, so now I would like to consider an example to illustrate all of these things that we have developed so far. In particular, this projection operator, how we use the projection operator to kind of classify the basis functions according to the various irreducible representations. So let's see what I have here. So that's the thing that I just talked about. Yeah, here it is. So again, we take the group S3. So this this group is isomorphic to the group, what is called the group D3. So that's D3 is just a group of that triangle, rigid triangle. So we are not allowing for inversion or a reflection. So we just considered a rigid triangle. So this is a rigid triangle, equilateral triangle, equilateral triangle. It's very difficult to write on this iPad because it's very slippery. I don't have control of what I'm writing. Yes, so it's okay. So this is the kind of visualizations of the group S3, if you like, and it's kind of obvious that that it is isomorphic to the group S3 because when we make a rotation, then it's just mean that we bring all these 3 points into each other. So that's just like a permutation. So when we let's say when we rotate around the z-axis, so the z-axis will be perpendicular to the plane by 120 degree, then it means that this point is brought to that point is brought to that point, and that point is brought to that one. So if I label this by, I don't know, let's say ABC, like that, well, that is just a permutation of A, B, and C. And so that's why it is isomorphic. And later, towards the end of the course, we will consider the permutation groups in more detail. And we have this famous theorem that any finite group of order n must be a subgroup of the permutation group of the same order, of course. So it's called Cayley's theorem. So just come back to this. Okay, so this is the S3 group. So now we want to choose some basis functions. So let's say that we want to kind of diagonalize some Hamiltonian of some molecules or so. Let's say that we have some atoms here at the vertices. The triangle is kind of artificial molecule here, but it doesn't matter. And I imagine that I want to introduce some basis functions for this group. One simple choice, so that's of course doesn't correspond to the molecule now. I'm just choosing some basis functions. So we can choose the Cartesian vectors. So Ex, Ey, and Ez perpendicular to the plane. We can choose any functions we like. So it's completely arbitrary, the basis functions, nothing to do with the group. It's something that we choose depending on the problem that we want to solve. So now we make a table like what we have here. We just list the basis, Ex, Ey, Ez, and we look at how these vectors, these basis vectors, are rotated when we apply the symmetry operator on them. So first one is trivial because it's just a unit element, doesn't do anything. And we look at C1, let's say. Now, C1 means counterclockwise. So usually the rotation is defined to be counterclockwise for positive rotation. So it's just convention. So positive rotation, positive angle means counterclockwise. Counterclockwise. So when we say rotation by 2 pi upon 3 or 120 degrees, it means a counterclockwise rotation. So we say that this Ex then we brought to somewhere here maybe. So that will be Ex prime, let's say. And Ey will be brought here. EY will be brought exactly here. So that's my new EY. And the Z component is not affected because it's perpendicular to the plane. So you're kind of beginning to guess now that this EZ kind of forms a separate subspace. They are not affected by the rotations around the Z-axis. Yes. So if we look at the effect of the C1, so that's a counterclockwise rotations, right, 120 degree on the EX, EY, and Z, then we can just easily figure out what that is. So we look at the EX, for example, I have this EX prime here, so then it will be minus 1/2 EX plus this component, which is square root of 3 divided by 2. And if I look at the EY, well, it goes here. So then it's equal to minus square root of 3 upon 2 EX. So this length here, this length here, it's a minus, plus it's to the left, and then we have minus half EY, and so on. So the EZ is not affected. It's just become EZ. And so on. You can continue like this. We are not going to go through this one by one. It's just the same thing. So we need to just take one example. Okay, so we have these transformations of the basis functions. So now we can construct the explicit representations of this based on this basis. So we have this here, that if I apply symmetry operation on basis vector, there will be a linear combination of the others. So the EX, EY, and EZ then forms an invariant subspace, but it is not necessarily irreducible. So invariant does not mean that it's irreducible. And in fact, you can see already from this result here that the EZ always go to itself. Yeah? So we know that that this EZ forms a kind of invariant subspace by itself. You can see this more explicitly. And let me erase this thing first. Okay. So we can then easily construct the representation matrices for the symmetry operators, TG. So for the unit element is obvious, it's just a unit matrix along the diagonal, it's 1, 1, 1 along the diagonal. And if we look at TC1, so just take one example here. So we see that if we take some, let's look at the EX, for example. So we take EI, and we have TG. Let's say EX here. So then it's just picks up the coefficients of EI of this vector here. So we already work out here. We have worked out the effect of this of TC1 on the various components. So we see that we get minus 1/2 and the square root of 3 upon 2. So these are just the coefficients of the vector of this vector. The x and y component of this vector. and so on. Yes, we can look at the components also. So it's quite straightforward. So we see then we have 6 matrices representing the group elements. So we notice already that it is in the block form. So we see that in the block form like this. The matrix is in the block form. Yeah, so this means that the representation is reducible. So let's check that and see if it follows the theorems. So let's calculate the characters of these representations. So there are 3 classes, so we will have 3 distinct characters. So the first one is just the unit element, and the character is just a trace of this, so that's just 3 then. And then we have the class, the second class, which is C1 and C2. So that's why I call it C1 and C2, so to indicate that they belong to the same class, C. And if we calculate the trace, so both C1 and C2 have trace 0, as it should be, because they belong to the same class. So elements belong to the same class, have the same character, same trace. So that fits with the theorem. And then we have the third class, which are this D1, D2, and D3. And again, you can see that all of them have the same trace, which is -1. Yes, if I just take TD1, for example, then the character or the trace is just -1. And that's the same for D2 and D3. So far we have not violated the theorems. It just follows according to the theorems. So that's nice. To worry if something doesn't fit. Means we have done the algebra incorrectly, not the theorems wrong. So now we want to decompose this representation into its reducible components. Of course, we can just already look at this directly, but we want to do this in a more systematic way. So we will apply the theorem, the orthogonality theorem, orthogonality relations, to decompose the representation into its irreducible components. So we write the character chi, or the trace chi, as the sum over the irreducible characters, like this. Yeah. Now we use the first orthogonality relations. So we calculate the coefficients M alpha using the first orthogonality relations. And to do this, we need the character table. So we see that again that the character table is very essential. That's always, all these characters always come up when we apply group theory. And it's quite easy to do this. So we calculate, for example, M1. So that's the alpha equal to 1. So H is equal to 6, and then that would be 1 upon 6. Okay. And then the number of elements in the first class is just 1. So that's 1 like this. And the character of the first representation for the first class is just 1. So again, it's 1 like that. And the character is 3, yes, because chi, the unit element, is equal to 3. So that's why we have 3 here for this one. And so on. So let me just continue. So I have the second one, so that's 2. So that's the number of elements in the class associated with the CC. this class C. So the character is 1. This one here. And the character of class CC is 0. So that is 0, like this. Yes. And then we continue. We have 3 or that one. And then 1 is this one here. And then we have -1, I think, for the, so the character of CD is -1. Yes, character of CC is equal to 0. So we just calculate this. It's easy, and we have it needs to be an integer because it's a multiplicity, and this is 0 because that's 3 minus 3, so that's 0. So this tells us that this representation contains no identity representation. There is no identity representation because M1 is 0. And we can continue the same, and we find that M2 is equal to 1. So I'm not going to do the simple algebra. It's very easy. Just plug in the numbers here. And M3 turns out to be equal to 1. So that's nice because all this multiplicity must be integers. So for example, if it turns out that this M is equal to some fractional, then we know that we have done something wrong. It has to be an integer. It has to be positive also, cannot be negative. So then we write that this representation T breaks up into 2 irreducible representations. So we usually write it like this: 2. There is only 1 T2 representation, and then plus, so then we do it like this, T3, like this. Yeah. So there is 1, so this is one-dimensional representation, one-dimensional, and this one, the T3 is two-dimensional, because these are the dimension of the representations, and that fits with what we had before, with the explicit forms of the representation, and we can see that they have a block form, 2 by 2 and 1 by 1. So the 1 by 1 is the T2 representations, and 2 by 2 is the T3. Okay, so this is how we break up, decompose the representations into its irreducible components. And we can see it's enough to work with the characters. So the character tables is very essential in working out the decomposition. So in the remaining time, I hope we have enough time here. I think we should have enough time. So in this example, we have taken the Cartesian coordinates to be our basis functions, or basis vectors. But it's really arbitrary. We can choose any functions we like. So in practice, I mean, if you think about solving the eigenstates and eigenvalues of some complicated molecules, then you need many basis functions, tens of thousands. So let's take another example, less trivial here. We just choose some arbitrary functions. We choose a basis. Now we start from an arbitrary functions. Let's say this x squared. And as I said, we can take any function we like. So we take x squared, for example. So you might notice that x squared actually belongs to In the atomic, if you do atomic physics, then you realize that this is part of the d orbitals of an atom. But in principle can be anything. We just choose x squared, so it's more complicated. So now we want to see how these functions transform under the various symmetry operations. So we want to generate the invariant subspace. So as we saw before, we can just take the function and operate it by the symmetry operators like this. So we have it here. So we apply unit element C1, C2, D1, and so on the x squared. And how do we do this? Well, we just follow the definition, our definition that g on the function f. We say that this is equal to f g minus 1 r, like that. So this means that we operate it on x squared. We can write x squared as ex dot r squared because we want to apply this on the r. So then that's equal to ex dot g minus 1 r, or I can also bring the g to the left. Yes, it's the same thing, like this. And then we can use the table that we have worked out before to calculate this dot product. So it's a dot product here. So it's quite straightforward. It's quite simple. So for example, if we take the C1, then it just becomes, sorry, so it should be squared here. It's squared here. So we see that this thing here is just that thing here. If you look at the table, and you just take the square. So we get that expression here, and so on. We apply this symmetry operators on the x squared. We get functions. Yes. So these functions, you can see that this thing and this thing are the same. So as we said before, that when we generate this invariant subspace, and some of the functions may be the same. So this is an example. And also we can see that this one and this one are the same. And this one and this one are also the same. Yes, so there are actually only 3 independent functions. So there are 3 independent functions, 3 independent functions. So from these functions, we can normalize them. Something funny here with files. It should be like this, I think. Let's square it here. So we have these 3 functions. Let me go back. So we have these 3 functions. Oops. X squared, this one, and this one. So these are the 3 independent functions. So from this we can construct 3 orthonormal functions by using, for example, using the Gram-Schmidt orthogonalization procedure. And if we do that, we get this result here. So I will not go through This algebra is just algebra. So we have one function that we start with, x squared, and then the second one is call it phi 2, and then we have phi 3. So now we can use these functions to construct our representations. So we have again a table of phi 1, phi 2, and phi 3. So now they are normalized functions. And then we see how they transform under the group symmetry operations. So we have it in the list here. It's not something we can easily see, but it is rather straightforward to work out all these results. It's just some simple algebra. So what we found here is that we see that if I operate C1 on phi 1, for example, then the result will be some linear combinations of phi 1, phi 2, phi 3 as we expected, and so on. So we see that we can construct representations. These are the representation matrices which we can easily construct from this table, like what we had before for the Cartesian basis vectors. So now we see that they don't have they are not in the block form. Yes, so it's a 3x3 matrix, but they kind of it's a jumbled. There is no particular form. They are not in block form. But we know that there is no three-dimensional representation. There is no three-dimensional representation. So then we can tell already that there should be some unitary matrix that will transform this representation. So there is another equivalent representations that has a block form, because we know there is no three-dimensional irreducible representation. And so to do this, apply the projection operator. I just have time here. So now we apply the projection operator on these functions. So I will not go through the algebra because they're just quite straightforward, but I just discuss the results here. So now if I take the representation 1, so this is the irreducible representation 1, for example, and I apply this projection operator on the function phi 1, so that's an algebra, then it turns out that we get this result here. So this combination, this is just a constant, so this combination, we know that that transforms according to the first representations, which is the identity representation. So this is the transforms according to the identity representation. So transform according to the identity representation. So if I apply all the group operations on this function, then it'll go back to itself because it's an identity representation. So you see, it's a rather powerful device here, this projection operator, because it allows us to decompose the functions into the irreducible representations. So if we do the same, of course, we already know that this is the function that transforms according to the identity representation. And so if we apply this to another function, here the phi 2, then we should get the same result, which is indeed what we found. So we have the same linear combinations. Yes. So we should not get another function that transforms according to the identity representation, because it's only one dimensional. So it's only one function. And if we apply to phi 3, it becomes 0. We can do also with P2 and P3. I think if you do P3, you don't get anything. So here's another example. If we apply this phi 1 to P3, we find these linear combinations. So then we know that this particular combination transforms according to the third representation. So this is how we figure out how the functions decompose to the different irreducible representations. Let me just use a few minutes to finish this. So now we can construct a new set basis functions. So this is the identity representation. Yeah. And this two then is belonging to the third representation. 2 by 2, two-dimensional representation. So we then have a matrix S that relates the phi basis to the psi basis. So this is the relationship between the psi and the phi basis. And the matrix is this S here. We can easily read off from this set of equations. So the important point is that this matrix S is independent of the group element. It is true for any group element. So the representations will be brought into block form by this transformation S for all the elements, not just one element. So we have an equivalent representation, which is now in the block form, in the psi basis. So that's how we work out the various irreducible components of an arbitrary functions. Okay, so maybe I should stop here. We are always gone over a little bit. So tomorrow we have an exercise class. So group 1 and group 2 as listed in the website. We should prepare for the solutions in the exercises. So the idea is not to put to make you under pressure or anything like that. The idea is just to make you get involved in the exercise class. So if you get stuck with the problems, it's no problem. It's not a big deal. So we just go through the problems together tomorrow. So okay. So if you have, I don't know if you have questions. And if you don't have questions, then we meet tomorrow for the exercise classes. So please prepare for the solutions in group 1 and group 2. Okay, bye-bye then. Goodbye.